Okay. Right, I believe we're recording now. Okay, so today is our last examples class, and I'll be going over the exercises that were for simulation. Okay, so let's just get started. So the first one is this problem of a simulator that models the arrival and departure of people from King's Cross Plaza. This is the example that I'd been looking at earlier in the video description anyway. And so you want to look at the number of people that are in the plaza and the dynamic evolution and the mean delay and the impact of changing the train schedule. So in some sense, the plaza is actually a buffer. So this is, if you were to model it, it actually sort of two servers or a couple, but let's just ignore it. So let's just say these are people arriving to plaza. And then these are the people who are departing it. And what you're not going to take into account is that the departure and arrivals actually are bidirectional. So let's ignore that for now. Because if people are arriving, they're departing, and they can depart by taking a train, they can depart by leaving the plaza and going off into the streets. And what we want to know is sort of the mean occupancy n bar of the number of people in the queue in the plaza, and then also the mean delay that you're going to experience over here, so the mean delay. And now, and the impact of changing the train schedule. The train schedule is essentially changing the departure process. So the arrival and the departure process actually. So it tells you how people arrive from trains onto plaza and how people arrive depart from the plaza into the trains. Presumably, if the train schedule is such that there are no departures, the train station will fill up and then they'll back up into the plaza and so on. So now you can see right away that if this were an MM1 queue, you would need to know things like the arrival process. You want it to be Poisson, otherwise it's going to be GG1 queue. It's complicated. If you have multiple trains going leaving, it becomes a multi-server queue. So you can have essentially a GGN system with n departures, and also you have a limited buffer capacity. So it's quite a complicated system, and one would be hard pressed to come up with a mathematical model for it. And so you'd say, okay, let's approximate it by using MM1 and just hope everything is okay. But if you have a simulation, you can actually simulate the exact process. And that's why we use simulations, because even though it requires more work, you can actually do it properly. So that's sort of the background for this. And so what we want to do is to know what is the state, what is the state of the system, and the counter variables. Now, so the state of the system, these are the variables. State variables are the ones which define sort of what's happening in the system at a particular moment in time. And the idea being that if you know the state, then just like in the Markov process, we can forget about past history. All we need to know is the state at that moment in time. And that tells us everything about the future. So that's the intuitive meaning of a state variable. It allows us to have a Markov type process. Now, in a simulation, it doesn't need to be Markov because you have the past history available to you. You can obviously go and look at the past history for as long back as you want to go. So the state variable in many ways are sort of a matter of choice. It's not something that there's a hard and fast rule of, because we're not doing Markov analysis. We're doing an actual simulation. So over here, this minimum you need from sort of in terms of state variable would be the number of people in the plaza, because without that we sort of don't have anything to work with, and that would be the state variable that I would choose myself if I were to do that. And then the counter variable is something that tells us, allows us to compute the performance metrics. And the performance metrics that we're looking for are the mean number of people in the plaza and the mean delay, which are the two things. And the third thing is impact of train schedule that just affects the performance metrics. So the performance for the two metrics that we care about, which are the mean number of people and the mean delay, for these two things, what we need to have is essentially for each person, we need to know their arrival time and departure time. And if you have these two, arrival time and departure time, then you know the delay. And then, of course, the first performance metric, which is the number of people in the queue, is you get automatically from the states. You don't need a control variable for that, but because already it's part of the state. And so this is the minimal choice of state and contour variables. You can make things a bit more complex. You can say, well, I don't need to know. So let's say that I have a counter variable, which is the second half counter variable, which is let's say the mean delay. So let's just call that a mean delay for MD for mean delay. And what we do is that we keep this arrival time and departure time only for people currently in the plaza. And then when they exit the plaza, we just add, so we have two things basically, the number of people contributing to mean delay, NMD. So when they leave, we add their delay to ND and we add 1 to NMD. And if we do this, then we only need to keep track of those that are actually on the plaza. And when they leave, you update these accumulative variables, and then you can forget about them because you don't need them anymore to compute the performance variables. Now, you probably also need to keep track of, if you want the standard deviation, you need MD square, so the sum of square as well. But yeah, but that's what you just need to keep these three variables, and then you know everything you need to compute the mean and the standard deviation of the variables. Okay, so I'll stop with that. Are there any questions about this?
In the method where we're maintaining the accumulator variables,
yes,
wouldn't we then have the arrival time and the departure time of the people currently on the plaza as part of the state variables?
Yeah. So it's strictly speaking, you can put it either in the state or the counter because it's a variable you need to maintain, right?
Mm-hmm.
I tend to think of counter variables as variables that are needed in order to compute performance metrics rather than inherently a part of the system description. But it's just a semantics over here. You do need to keep track of that. Essentially, for every person who's on the plaza, in the plaza, you need to keep track of that. You can call it a state variable or a counter variable, but it's a variable you got to keep track of.
Right. Thank you.
Yeah. So again, the distinction is purely in terms of semantics. Is it something that's intrinsic to the system, or is it something you're adding so that you want to compute a performance metric? And if it's intrinsic, we tend to call it a state variable. If it's something to compute a performance metric, call it a counter variable. Okay. And so so just to be very clear, so on departure, when you have this ND, so you're going to say basically say ND plus equals the delay of the, let's say this is the departure of, let's say, jth customer, delay J, and then you're going to do ND square plus equals delay J squared, and then NMD plus. So this is what you're going to do on the jth person, and then we'll reset delay J to 0 because we can make it available for somebody else to use later on. The jth customer is departed, so delay J, you can sort of free the delay Jth entry of your array or whatever it is you're doing. So this would be like the pseudocode you would use to keep track of things. And in the end, when you have basically the mean delay is going to be MD divided by NMD, it's going to be the mean delay, and then the formula for standard deviation is, I can never remember it, but it's basically sum of squares minus the mean squared, something like that, but you can look it up. Okay, any other questions? All right, okay, so let me move on to the second question then. And so here, you have a discrete probability distribution, and this is really a very trivial question. We are looking at this vector over here. So it's 0.1, 0.3, 0.2, 0.1, 0.3, And so we want to know how you generate the values from this distribution. Well, what we do is we compute the cumulative. So what you're going to do is, sort of visually speaking, we're going to look at the range from 0 to 1, and the cumulative is going to be 0.1, and then it goes up to 0.4, 0.6, 0.7, 0.7. So, and then it goes to 1. So you have these jumps. 0.6, 0.71. And then what we do is we generate a uniform random variable in this value range over here, and then essentially we sample sort of in this direction. And depending on where it lies, we're going to give the output. So if it lies, for example, if it lies in the range, so that this is the cumulative distribution F. So if Fi minus 1 is then equal to uniform random variable is less than equal to F sub I, then we will output xi, output the value xi, the discrete distribution value xi, and where f minus 1 is defined to be 0. We've got to be careful about that. F minus 1 equals 0. Okay, so any questions on that? Okay, yeah, that really was simple. The next one is also just pretty straightforward. So here we're trying to generate arrivals to the Poisson process, and so the Poisson process looks something like this. We have time on this axis, so we have the 0th arrival at time 0, and then we want to look at these gaps: t0 to t1, t1 to t2, t2 to t3, and then t3 to t4. And so the next arrival, so this is at time 0 sort of by definition. And then we want to look at the arrivals, and these gaps are distributed according to an exponential distribution. And we know that the exponential distribution, to go from uniform to an exponential, we basically are going to take -1 over lambda log of the uniform random variable. So that's what we're going to do over here. And in our case, lambda is 5. So this is going to be -1 over 5 log of u. And so here we are given the values of u1, u2, and u3 to u4, so u4. And so if you plug that in over here, if my answers are correct, then t0 is 0, t1 is going to be 0.413, t2 is going to be 0.413 plus 0.092, which is going to be 0.505. T3 is 0.505 plus 0.037, which is 0.542. And then T4 is 0.542 plus 0.283, which is equal to 0.825. So those values are basically these ones over here. So this is 0.825, 0.542, 0.505, 0.413 on this axis that I drew earlier. So that's basically the, okay. Does that match what you've done?
Can I ask a quick question, please?
Yeah, sure.
So in the notes, we do define that the easiest way of working out a Poisson random variable from that uniform distribution is to use that 1 over lambda log.
Yes.
But like about 4 slides before that,
yes,
you define a sort of more iterative process to find that Poisson
yes
random variable.
Right.
But when I used that, I got like really different answers.
Oh, okay. Let's see. So I'm looking at the slides right now. This is slide 22. So what we're doing over here, let me just use my screen over here to point out. I mean, okay, so we said t equals 0, I equals 0. So this is going to be I equals 0, and that's t equals 0. We generate a random number u, that's going to be u1. And we said t equals t minus 1. So that we're basically adding to this. So t1 is equal to t0 minus 1 over lambda log u. ln, it should be log natural actually, because this is exponential, right? So ln, maybe that's a mistake, but anyway. And then if this is greater than the value t, capital T, we stop, right? If we don't stop, then we're basically going to go to set t1 to this value over here, to this value over here, and we repeat the steps. You compute the next jump over here and the next jump over here, and so on. Where do you differ? Maybe I think we're right. The log, it says log, and really should be ln, shouldn't it? This should be ln, log natural, not log base 10.
Yeah, can I quickly come back to that in a minute when I found the actual slide?
It's slide 22, but yeah, sure.
Yeah. So on slide, we have on slide 22.
22, yes.
That's simulating a Poisson process. But
right.
What's the difference then between simulating a Poisson process and finding Poisson random variables? I think was my question.
Okay. So a Poisson process is a sequence of arrivals like this. This is a Poisson process. This sequence over here is a Poisson process. And Poisson arrival is basically just one step of the Poisson process. This is Poisson arrival, but the Poisson process is the sequence. I mean, again, it's a matter of semantics. But what the slide is saying over here is that we would like to know what if you're given a time t, you want to generate the first capital T time units of a Poisson process. And so this tells you what to do. You keep generating and you say, oh, good, I got to the end of t, I can stop now.
Okay, but if it's the case that we're generating a random Poisson variable, then we should expect those singular time steps. So not necessarily the aggregated time by taking the sum, but the single time steps to be comparable. Surely.
Yeah. So each time step is coming from x sub I. If you look at the x sub I equals -1 over lambda log ui. So that's where each time step is coming from. So for a Poisson process, the inter-arrival times are exponentially distributed. So we are just choosing. So let me just draw this again. So yeah. We have some time over here, and I want to say, okay, generate a Poisson process for the first t time units, because my simulations of length capital T, and I want a Poisson arrival, so generate all the arrivals time for me, right? What you're going to do is you start with time t0, which is 0, and then you generate a value which is drawn for an exponential distribution with parameter lambda, and that tells you the first arrival time, which will be t1, okay? And then you draw another value from the exponential distribution, which is also from the same parameter lambda. It may be longer, it goes to t2. And you keep doing this until you draw a number and you say, oh, wait, the sum of all the times exceeds capital T, so I'm done. These are the values that I want over here, Tn. That's what the algorithm is saying on page 22, on slide 22.
Thank you for that.
Okay, good. No, does that answer your question?
Yes, thank you.
Okay, great. Any other questions? Okay, and again, intuitively, what's going on is the same thing that we have, which I showed over here. So if I draw this for the exponential, basically what you're saying is that we are going to have this exponentially. So the function. So actually, we can just do it for an arbitrary function. What we need is the arbitrary density function. So we start with the density function, which could be anything, and then we convert that to the cumulative, which is going to be monotone and sort of going something like this. And then we sample it, and we know that it goes from 0 to 1. So the y-axis goes from 0 to 1, and the x-axis goes over the support, which is the smallest and largest possible values of the density function. And then what we do is we're going to sample a value 0, 1, uniform 0, 1, and then we look this way. And what you'll see is that if we have like a jump in this over here like this, that corresponds to a jump over here, then we're more likely to get something that's in this range over here. Whereas if you have something that's there is, you know, where there's, if you take an extreme value, let's say that I'm going to just redraw this over here. Let's say that I have something, I have a big jump over here that's flat, something like that. In the cumulative, it will look different. The cumulative is going to be, over here, it's going to go up as a value roughly linear. And then on this, when you have the jump over here, we're going to get a jump in the cumulative as well, because it's going straight up. And then after that, the cumulative isn't changing much in this regime over here. So it kind of stays flat over here, and then it goes up again, something like that. I should have chosen a slightly better thing. This looks almost a cumulative already. Let me draw this properly. So what I want is something that's relatively flat, and then there's a jump over here, and then sort of relatively flat again, and then goes down to 0. So that's your support over here. The cumulative is going to look like this. When you have this jump over here, you get a big spike in there, and then when it's flattish, it's going to stay flattish. Now, when you go look this way, you're going to get a lot of mass, a lot of higher probability of choosing something in this particular range, which is just what you'd like, because that's where that spike in the density function is. So that's sort of intuitively what's going on with this way of simulating. But it's a very nice trick when you can find a cumulative density function, you can invert it and you can do it. And of course, as you saw earlier, you can do this for arbitrary empirically derived density functions by using this approach over here. So where you compute essentially the histogram, and for the histogram, you can work backwards and generate numbers from an arbitrary distribution for the simulation. Okay, any other questions? Okay, so let's move on. So the next one has to do with sort of revising some of your statistics. What we want to do here is we want to compute basically we want 95% confidence that the value you're computing is plus minus 10 people of the value that you estimate from simulation, plus minus 10 people of the mean. So the way we're going to do this is, and I think actually it's in stopping rules, it's on slide 32. So essentially it's exactly the straight off from slide 32. So intuitively what's going on is that we have some distribution which is centered on the mean X bar, and then we have some distribution around it. And what we expect is that the distribution is going to look, if you run it enough times, each time the X bar is sort of the mean of means, mean of simulation run means. And the mean of means has the property that it's normally distributed as when the number of runs is large. So the simulation run mean itself is descriptive of the distribution of the underlying parameter. So that could be arbitrary, but the mean of means, which is called the distribution of the means, that mean of means is going to be approximately normal when you have a large enough number of runs, and which means that we can bound the area over here by the normal distribution, and in particular by the standard normal distribution denoted Z, which is n normal to 0 mean and a variance of 1. So and so that's basically the rule we're going to use over here. So to get this to work, we have two things we need to worry about. First, we need to have enough runs so that the distribution is approximately normal. Distribution is reasonably normal. The distribution of simulation run means. This means I'm talking about. Means is approximately normal, and then the second, and the actual stopping rules itself. So that's why the solution work has two parts to it. So first, we run the simulation enough times. So enough is usually, so the people have found that it has to be more than 20, and about 100 is a good number. So at least 20 is minimum, like about 100 is good. And so typically we use 100 is what is good practice, best practice, a number of replications. These are the replications that we have. And then second, we use the stopping rule. Once you've done this, we think, okay, it looks sort of normal-ish. Then we're going to compute the mean for each thing. So let's say xn bar is the mean value of the, xi, so let me note this properly. So let's say we run n simulations so far. It's n simulation runs, and we are going to compute xi is the mean number of people in Plaza for ith run. And then we'll denote the mean of these values, which is basically sigma xi by n. We'll denote that as xn bar. And then we compute the quantity Sn, which is sigma I xi minus xn bar square by n minus 1. And this is sort of approximately the empirical variance. And the confidence interval we want alpha is given by 0.05, that's 95% confidence. And so we want basically 2.5% on each side. So we want 2.5% over here, 2.5% over here. And that's the variate Z minus 0.025 and Z plus 0.025. Oops, 0.25. So these are the variates that we want, and these happen to be minus 1.96 and plus 1.96. And so the stopping rule basically says that compute the value twice, because we're doing it on either side twice, 1.96 Sn by square root n, where Sn is this value over here. And if this number is less than, if this value is less than 20, then stop. And that's basically the that's saying that, okay, we think we have enough confidence. So the number of people who are in this range is less than 20, because you're plus minus 10 in each side of the mean. So we're allowed to have plus minus 10. Okay, any questions about this? All right, looks like you're up on your statistics. Good, that's excellent. All right, so then the fifth one is about how could you use antithetic variables to reduce the variance in your simulation runs. So the antithetic variables are basically variables which are negatively correlated to each other. And in fact, on slide, on slide 37, I believe, or 38, right, 38, it tells you what to do for this. So remember, we have a bunch of replications. So the first run, let's say we use variables u1, u2, etc., un for the first one. The second run, you would use basically 1 minus u1, 1 minus u2, etc., all to 1 minus un. And then the third run, you go back and repeat the whole thing. So essentially, for all even numbered runs, you do 1, and for all odd numbered runs, you use 1 minus un, and that should reduce the variance in your simulation, which means that this computation will actually be will terminate faster than if you just generate new random variables each time around. Okay, any questions about this?
I have a question. So just to confirm, so when we, so once we do this method and we calculate
Yes.
the sample variance, we just use the same formula, right? There's no change to
Yes,
that.
that's right. Yeah, that's right. This is just like a trick that simulator, the people running simulations can use to reduce the variance of the simulation. Yeah.
All right. Okay, cool. Thank you.
Sure, you're welcome. Okay, and then the problem six. Okay, so this one actually I want your help with. Okay, so here's what's going on. Somebody is looking at a simulation. They build a, they do everything, and they own random number generator using custom code. And they say that, hey, I'm running a single long simulation run, and it doesn't really match what's going on. So why might be, what might be the reasons? And I could come up with, let's see, 1, 2, 3, 4, 5, 6, 7 different reasons that why it might be wrong, why it might be off. But I don't want to give you my answer. I'd like you to tell me what your answers were, and I'm going to write it down. And I'll see if you got all the 7, or maybe you came up with more that I hadn't come up with myself. So what might be the reasons why simulation results don't match reality? Anybody wants to just unmute yourself and go for it?
The custom code the person is using might be buggy.
Yeah, okay. So how would you counteract that? How do you make sure that the code isn't buggy? Or can't make sure, at least how do you test that the code isn't buggy? So the way to do this is that the simulator typically has sort of 2 parts to it. One is sort of the simulation engine, which is the arrival of events and random number generation and all this other stuff. And then you have the part of the simulator which deals with the actual data center, the switches and the links and so on and so forth. And so what you typically should be doing, very few people do it, but you should be doing, is to use your underlying engine to simulate a well-known result like a MM1Q, all right? And then if you can simulate an MM1Q with your engine and your results match the MM1 results that you expect, then at least you know that your underlying engine isn't wrong. It could just be the buggy code. So so you should always debug using Actually, you can do it in 2 steps. First, one is using like an MM1Q. And then the second thing is using what's called a micro benchmark. And in a micro benchmark, you know what the result is going to be. You know exactly what the output is going to look like because it's trivial, right? It may be a very, very small queue, very, very small system, a single switch. And you can look at it and say, yep, that's what's supposed to happen. And if you can't simulate a micro benchmark, the rest of it isn't going to work either. So in practice, you should always do both this and a micro benchmark, and then you'll be able to see. Okay, so that's one. What are the possible reasons to be wrong?
The fact that they use their own random number generator could
Indeed.
lead to the fact that there's not
Exactly.
actually true randomness.
That's right. Absolutely true. So randomness generators are very finicky, and people find after the fact that what they think was random wasn't really random. And so it turns out that getting a good random number generation is very, very difficult. And so it's best to rely on a standard library than to do your own. And in fact, these libraries values are also, they keep improving them based on physical phenomena and things like that. But yeah, very good. Okay, let's keep going. That's 2. What else?
The user might have ignored the warm-up period for the process or the simulation.
Right. So this is the warm-up. So it is necessary that you run it long enough so that the initial transients go away. And so the initial system is a sort of a non-equilibrium state. You can think of this as Q. If you think of a Markov chain, you have these initial transient states, and then you get into the steady state, into the ergodic part. And so we want to get past the transient states. So we need a long enough warm-up. Very good. And any other?
So the engineer might have got their model wrong. Say the actual case might be an open system, but he modeled a closed system.
Very good. Yeah. So as I discussed in the video quite a bit, yeah, we have to model the closed and open system properly, and they could have gotten parameters from a closed system and moved it to a different closed system, and then it's not going to work, right? So it's important that especially the population is small and the system is closed, then the arrival process should be reflecting this. And so we should try very hard to get open system parameters rather than closed system parameters for traffic. Okay. Anything else?
The fact that we're using a single long simulation
Indeed.
run.
Exactly. Yeah.
Cause
As I mentioned earlier, we want to do lots of replications, as many as we can afford, because the central limit theorem only applies when you have enough replications. So if you're doing a single long run, then you're not really guaranteed. Now, again, if the system is ergodic, we know that the single long run is just as good as a multiple initial runs. If you think of it from the perspective of queuing theory, single long run is identical, but the system may not be ergodic. That's the whole reason we're doing a simulation, perhaps, is because it's non-stationary, non-ergodic. So we do want to, single runs are a bad idea, especially for non-ergodic systems anyway. All right, what else? There's two more I came up with. Okay, so I'll give you two more. One is that the simulation is only good as its parameters, right? The parameter choice. So when you're modeling a data center, you're going to have to model things like how many buffers are there, what's the link speeds, all these kinds of things. So so if you make any mistake in the parameter choice, then you're going to have mistakes in the simulation as well, because you're not going to be able to model the right thing. You may say, oh, I think the buffer there is whatever, 2 megabytes. It's actually 20 megabytes. You're going to have mistakes. And so you need parameters correctly reflecting the physical system. And then the other part of it is that every simulation is of a model. Okay, simulation is of a model. And as you now know very well, a model is not reality, right? We're going to ignore certain aspects of reality in order to model it properly. We are going to, for example, assume that the arrival process is Poisson, or that the system is ergodic, or that if we have a control loop, we're choosing the right control parameters, etc. So the parts that you ignore may be important. And so I'll give you a very specific example. Just let me write this down. So let's say that we're modeling a CPU server. So we say, all right, we know what to do. Here's our standard buffer. We're going to have a link. It's a server. That's your CPU. So jobs arrive over here. We know how to model this. I studied this at Computer Systems Modeling. I know exactly what to do, no problem. And so you say, oh yeah, the service rate, this is something is mu, and your boss is impressed because you're using Greek symbols. The problem is this CPU is actually doing dynamic voltage and frequency scaling, or DVFS as they call it. And what this means is that the CPUs today, in order to save energy, actually their service rate mu is variable. It depends on time. It's not constant. So if the CPU is not heavily loaded, it actually slows down. You change the voltage, which is a controller, and then the frequency goes down. That's why it's called frequency scaling. And that uses less energy. And when it has more load, then you up the voltage, the frequency goes up. And so the clock cycle time actually changes over time, which means the CPU mu t changes over time. And if you weren't aware of it, You just say, yeah, I'm going to model this as a mu-t, and in your simulation, you're just going to go and model it as a constant rate server, which serves its job at a particular rate in time. But in fact, that would not be correct. So because of voltage scaling, you're going to have a variable rate. So the parts that you ignore may be important because you didn't initially model DVFS, and you find that it didn't work. So to sum up, all of these 7 reasons and perhaps more are going to possibly make it difficult for you to match your simulation output to reality. And so even if you have the most accurate simulator, you still have to get all of these things properly taken care of. So simulation is, again, not it's much more realistic than queuing theory and control theory, but even there are lots of problems. Okay, so any questions or comments on that? Okay, well, I'm not hearing any. So, okay, well, I think that, whoops, I don't know what happened. Okay, all right, I'm just going to, so that pretty much concludes the, I'm going to stop this. Okay, so that pretty much concludes the course, or at least the examples class. And also this is the last meeting we have for the course. So on Thursday is the last assessment, and I hope to have it graded by the first part of next week, which means I should have the final marking and stuff back to you next week sometime. And that's it, so the end of term. So thank you all for being part of the course. I have to say, you guys kept me on my toes. I learned far more about queuing theory and control theory this time around than I did when I was writing the book, I think. But it was fun. It was tough, but it was fun. I hope you enjoyed the course too. So I have one last request, which is that I did circulate this survey. So if you have a moment, please do fill it out. It's helpful for me to have that feedback when I try to plan out next terms, next time I teach this course. So thank you.
Thank you.
Thank you.
Thank you.
Thank you.